So,
He passed.
did he?
Yeah. Who? James. Woo! Go James! Pass the driving test.
No, it's COVID test.
Okay, so we have with C, I think we've done A and B, haven't we? So we're on to C. We have C. I have to say I've never seen this with a question like this before. So I've seen plenty of questions where you get no solutions as a result of when you solve the quadratic, getting values for cos or sine that are bigger than 1. But this was a really odd one, wasn't it? I mean, what happened, George, when what did you do? What did you substitute?
So, first of all, I made it easier. So I made it 6 cos squared theta.
Brilliant.
6 sin squared theta equals 0.
So 6 cos squared plus 6 sin squared theta. I'm just realising I'm writing in blue, which probably isn't visible on the screen, and I have brought a black pen with me.
There's a green one there.
Yeah, that's not going to work, is it? Okay, and then carry on. What did you do at that point?
Then I obviously turned 1 in, so I used sin, so I turned that into 6 times 1 minus cos squared theta equals 0, which gave me 6 equals 0.
Yeah, so you end up with 6 equals 0. Now, quite clearly, because you get minus 6 cos theta there, 6 does not equal 0, so we've got no solutions. Now, I have to say, that's the first time I've ever seen a question where you get no solutions at that point. I've seen plenty where you get no solutions after the quadratic, and you must never be afraid of that, but in this case, yeah, that was a slightly odd one. Now the last one was a bit more straightforward, but I am going to go and get a black pen. Sorry, so I'm going to pause the video. So as you were scribbling so furiously, Isabel, it'd be rude not to pick you, wouldn't it? So,
Sure would.
what did you substitute in this very last one?
I replaced sine squared theta for 1 minus cos.
Brilliant, yeah, and of course you had to do that. Where with the others there were a couple of options, but with that one you had to do that, didn't you? You had to do that. So it all falls out like that. So we end up with our minus 2 cos squared theta plus 12 cos theta, and we've got 2 take away 7, which is 5. I'm desperate to multiply by minus 1, but I'm not going to. So what do we get when we use our calculator to solve that? Go for it, Lily, tell me what you get.
What the actual solution?
I've got the cos theta solution.
6 minus root 26 over 2.
So 6 minus
Root 26 over 2.
root 26 over 2. Just that one?
Well, the plus didn't have any.
Okay, so I'm going to write it down anyway, and then I'm going to indicate.
It's like 5 or something.
So this is a big old number, isn't it? You know, that's 26, root 26, almost root 25. So we know straight away that's not valid, which is great news, isn't it? It's always great news. So we've got this one, which is valid. And is that going to work? No, of course it's not going to work. I'm just having one of those days. So, no, and I'll try the left mouse button. There. Oh, what on earth have I done there? 1.1 and 5.18. I don't know what I've done there. I've got in some sort of debug mode. There we go. Excellent. So we have solved trig equations where we're starting to use radians. And actually, until this very last step, the radians were irrelevant. Well, you know, this bit hadn't changed from when we did it last year. It was only at the very end, when we did shift cos, that we had to start thinking, right, I'm not working between, this was cos, 0 and 360, I'm now working between 0 and 2 pi. And we are going to work with both radians and degrees. Don't think degrees are being consigned to the dustbin of history. We still have plenty of questions where we're expected to work in degrees, and the difference, well, Pat asked that really sensible question yesterday, how do you know? Well, it will only be here in the range of values. So if it says 0 to 360 or minus 180 to plus 180, then that's a degree question. If it's a reference to something to do with pi, then that's going to be a radians question. Okay, there's one more thing we need to do with radians, and then we draw a line, because I've said I won't ask you anything after radians in the mock paper. So, and that is called small angle approximations. So pop that as a little title, but then I'm going to show you some graphs, and for that I'm going to calibrate the forward. Now the good news about this bit is that it is all on the formula sheet. Well, everything you need to remember is on the formula sheet. So, so that makes it a little bit easier to deal with. So I'm going to draw you a couple of graphs, and I've set up a set of axes in radians. So I'm going from 0 to 2 pi in 45 degree jumps. Pi over 4 is 45 degrees, pi over 2, 90 degrees, etc., etc. So here is the graph of sine x, y equals sine x, okay? So I'm going to write that on the board. Where's my little tin? And on that same set of axes, I'm going to plot the graph of y equals x. There it is in blue. Now, if I was working in degrees, the y equals x line is the line that goes through 0, 0, 1, 1, 2, 2. If I was working in degrees, remember this is 45 degrees, so 1, 1 would be about there. So the y equals x line would be a much, much, much steeper line if I'm dealing with degrees. Because I'm dealing with radians, where 1 radian is about 50 degrees, so that's at 57 degrees, which is about there. The line is a lot less steep. And what it means is that for the first few radians, y equals sine x and y equals x run pretty much together. In this sort of region here, they're the same. And what that means is that if we're in radians and we're dealing with small angles, the size of the sine of an angle is about the same as the angle itself. And we can test this on our calculators. So if you do for me, make sure your calculator's in radians, the sine of 0.1. No, the sine of, so just sine of. You get a number that's pretty close to 0.1. I get 0.099. And if I do an even smaller number, say 0.05, the sine of 0.05, the answer is very nearly the same. So for small angles, the value of the sine of an angle is about the same as the angle itself. Now, as the angle gets bigger, so if I do, for example, the sine of 2 radians, that is nowhere near 2. So this only works for small angles. Now, when we did the binomial series expansion, we had a definition of small. We said the x in that bracket had to be between -1 and 1. There is no definition of small with this. It's a rather vague thing. And you're never expected to sort of comment on how accurate it is. But yeah, for small angles, and you can see that up until sort of 20 degrees, it's pretty much bang on. So if we're working in radians, for small angles, the sine of the angle is about the same as the angle itself. Now that's quite useful in some situations, because there's lots of people who are interested in little angles. For example, if I take the cover off my speakers in my living room and play some music and watch the speaker, I can't see it move. But as soon as I put my hand on the cone, very carefully, obviously don't want to damage my speakers, you can feel it vibrating. It's moving by a very, very small angle. So if I'm an acoustics engineer wanting to, develop a better speaker, I'm dealing with small angles. And there's lots of things that move in small ways. Any sort of vibration tends to be a small angle of movement, and some vibrations are good, sound engineers, some vibrations are bad. Airplanes, vibrations tend not to be very good. So this sometimes makes complex calculations a little bit easier. So that's true for sine. What about for the other trig functions? Well, let's go with tan. So I've left my y equals x line up there, and in red plotted the tan x, again in radians. And can you see how, again, for small values of x, and I know I'm using theta here, that's because they use theta on the formula sheet, for small values of x, it's about the same. So I can also say that, right, for small angles, the tan of an angle is pretty much the same as the angle itself, if I am dealing with radians. Now there's always someone that spoils it, isn't there? And yeah, cos really spoils it. So okay, we can't use the y equals x line. The cos of an angle isn't going to be the same as the angle, and we know this because the cos of 0 is 1. Couldn't be more different. But I tell you what, this shape here looks a little bit familiar.
Y equals minus 9x squared.
It looks a bit like a parabola, doesn't it? Yeah, no, it's an upside down parabola, so it's y equals minus x squared. So let's have a go. Okay, so if I type in y equals minus, I think I'm going to put my x in bracket, x squared in brackets. That's okay. I'm not. What have I got to do to it now? Well, it doesn't. With the x squared, there's no trig going on, so that doesn't matter.
Add 1.
Add 1 to it. Okay, we'll add 1.
Minus 1. Yeah, add 1.
Still not very good, is it? It's. We've got to make it 1 now. So what do we do to make it stretch in that direction?
To the x.
Just the x. And what would I, say I wanted to make it twice as wide, what would I multiply the x by? You multiply it by half, wouldn't you? That's right. Now actually we don't multiply it by half, we multiply it by 1 over root 2. And if you do 1 over root 2 x times 1 over root 2 x, you get a half x squared. And that's what we use. We actually put a half outside the bracket and we say it's... And that's not bad, is it? That's not bad. For small angles, this part of the curve is pretty much bang on the cos curve. And you could argue, well, if you made it a little bit wider, it'd be easier, but half is a nice, easy round value, and don't forget, we're approximating here. So for small angles, cos of theta is equal to 1 minus half of x squared, or half of theta squared, which, when it's on the formula sheet, looks like that. Now, because I should say squiggly equal sign, shouldn't I? Because we're saying they are roughly the same as. I promise that by half term I'll get you your physical copy of the formula sheet, but it is on OneNote, and if we have a look at how that appears on the formula sheet, don't be afraid of scared of all the other stuff. It looks like that. So that's all on the formula sheet. You've got nothing to remember in that regard. Sorry?
What does square root mean?
It means roughly the same as. Not equal to, but roughly equal to. Right, so how will this appear then in a question? Easy peasy. So it will look like this. There'll be no context. It'll just say, okay, for when theta is small, no specification about how small or how big, just when theta is small, find the approximate value. So I'm going to use those three approximations. I'll do these two and give you then a chance to have a go at some for yourself. So for the first one, I've got sine of 2 theta. Well, if sine theta is roughly the same as theta, sine of 2 theta will be roughly the same as 2 theta. So that's going to become 2 theta. The tan of theta is roughly the same as theta. That means the tan of an angle is roughly the same as its angle. A bit of simplifying. 2 theta plus 1 theta is 3 theta. And the thetas cancel out, so I get 3 over 2, 1.5.
That's so weird how that works.
Well, let's test it. Let's test it. Let's make theta small and work this out. So let's go back to theta is a half. So, no, not a half, 0.1. 0.1 radians, that's about 6 degrees. 1 radian is about 60. So if I type that actual sum in, I'm going to type in the sine of 2 lots of that, which is 0.2, plus the tan of that, divided by 2 lots of that. So that's the exact answer, and we're saying it's going to be roughly 1.5. See how close you are.
Pretty accurate.
It's not bad, is it? I think it's to 2 decimal places it's accurate. Is it 495 or something like that?
Yeah.
And 0.1 radians is about 6 degrees. So I reckon that if you're desperate for a definition of a small angle, single-digit degrees. Okay, single digits of degrees, which takes you up to about 0.2 radians. So 0.2 radians is about 12 degrees. So I reckon that's what I would say, but it's never an issue. Let's do the second one. Cos is always fiddly, always fiddly. So I know that the cos of theta is 1 minus theta squared over 2. So that means the cos of an angle is 1 minus that angle squared over 2. The angle in this one is 4 theta. So that's going to be 1 minus 4 theta squared over 2, which, as we know by now, hopefully, you've just got to be a bit careful about, because it's not actually 4 theta squared, is it? It's 16 theta squared. That's divided by the angle itself, theta, times the sine of 2 theta, which is just 2 theta.
Cheers.
Well done, James. Well done. I We're all going to lift home with James, aren't we? Did you drive here, or?
I don't know what, driven back.
It's always supposed to be the most dangerous time after the. Well done.
Thank you very much.
We're just finding out that when you're in radians and you're dealing with small angles, you get this really odd effect. The sine of an angle is roughly the same value as the size of the angle itself, and the tan of an angle is roughly the same size as the angle itself, and the cos of an angle is nowhere near the same as the angle itself, but you can get it by that rough calculation. So if you watch the video, you'll see how I derive that from the graphs. So I've got here 1 minus, oh hang on, I've got a minus 1, sorry, I've got a minus 1 here, got that. So I've got here 1 minus 16 theta squared over 2 minus 1 over theta times 2 theta is 2 theta squared. So you end up with the 1's disappear. You get minus 16 theta squared over 2, which is minus 8 theta squared. So I've got minus 8 theta squared, I don't know if you can see this still, Grace, on the camera, over 2 theta squared, which works out as minus 4. Minus 4. just about, see. So 4 theta times 4 theta is 16 theta squared. Divided by 2 is 8 theta squared. The 1's cancelled out, so I was just left with minus 8 theta squared on the top. Divided by 2 theta squared is minus 4. I won't get you to substitute a value in, but you get a fairly similar answer. Now, I didn't bring the books because I really don't think this is worth doing a lot of practice on, but go on, have a go at those 3. This is on the formula sheet, James, so you don't need to remember it. Just gonna rewind for grace. So for this one here, you've got 4 theta, take away 2 theta over 3 theta. Right, so for this one, I've got 1 minus cos of 2 theta. So cos of 2 theta will be that. So I've got 1 minus that. But that minus, remember, multiplies everything in the bracket by 1, minus 1. So I've got 1 minus 1. But minus that, so that makes it positive, yeah. And in the last one, you just end up with 2 theta over 2 theta, which is just 1. So I mean, it's nothing to do with trig. It's just algebra, and nothing to remember because it's on the formula sheet. So it's one of those things that really is a sort of weird but not hard. I'm doing vectors with my year 11s at the moment. That's weird but not hard. You know, it's this is definitely in that sort of category. And I'm not going to do any more. I mean, there's another question on page 134 if you would like, or a couple of questions there, but I don't feel it's worth doing. So we have covered an introduction to radians. We've looked at the application of radians in circles and with sectors and arcs, triangle problems. That included a revision of particularly the area of a triangle when you know about the corner, half BC sine A or half AB sine C, however you learnt it. And does involve a little bit of potentially cosine rule and sine rule, so you need to make sure we're okay with that. We then applied radians to trig equations, so rather than dealing with 0 to 360, we're now dealing with 0 to 2 pi, or sometimes it's slightly less. And we looked at this small angle approximation. So I'm now going to draw a line and say, right, there won't be anything on the mock, which we have covered after this. Everything up to this point, but nothing after this. And but we're not going to stop the lesson there, obviously.
Oh, we might as well.
No, we must not. No, we're gonna barrel on, and we're going to barrel on with something which sounds really, really exciting and impressive. Isn't really? But so we're going to move on to reciprocal trig functions. Now we've got 3 trig functions: sine, cos, and tan. So what we're talking about here is 1 over sine, 1 over cos, and 1 over tan.
This is a whole new thing.
Well, it is a continuation of trigonometry. We've got an awful lot of trigonometry to get through. So yes, it will work in both radians and degrees. But as we've just been doing radians, I'm going to stick in radians as I work through this. But what we are doing as part of this is we are going to load up our I Love Trig sheet with a couple of other identities. So I've given you all a whiteboard, and I'd be grateful if on that whiteboard you could sketch the graph of sine x between 0 and 2 pi. So just sketch the graph of sine x between 0 and 2 pi. I haven't. Has anyone got a? Does anyone a little squirt of a?
Oh no!
It's there for it. I'll tell you what.
You have a break on whiteboard.
I'll tell you what, Charlie. Have you got a grubby one as well? I'll tell you what you need. What you need is I boil washed these this week. So that, although they still look green, they are actually really green.
The Sine.
Can I, sorry, but on a complete tangent, I've just bumped into another student in the corridor. If when you look at your UCAS form, you are surprised at your projected grade, i.e. it's not as good as you'd hoped, can you check with me, because I've come across 2 students whose projected grade was not as good as I had put on Unifrog, so something's happened with the whole Unifrog to UCAS sort of transition. So, and also I'm aware that I haven't had a discussion with a number of people post the mock we did recently, so I think there is probably room for a bit of movement there. So yeah, so please make sure you have that discussion. So I want, Radians, yeah. So Lily. Oh yeah.
It's already gone as well.
I already like it's gone, sir.
No, well, it hasn't, because Mr. Collins said.
No, it
He
has.
sent it.
Oh, right, okay. Actually, no, hang on a minute. Mr. James. Yeah, that was nothing. He asked me what yours was. So I said, yours is correct. Yeah, yours is correct. Right, okay. So what I'd now like you to have a go at sketching is 1 over sine x. 1 over sine x. Now, that's a really tricky thing to get your head around. So think about point by point, okay? So for example, think about what do you get when you do 1 divided by 0? Because here the graph of sine x is 0. So the 1 over sine x, you'd have to work out 1 divided by 0. What about here when the graph is 1 divided by 1? And here when the graph is 1 divided by minus 1. And then you can start to think, okay, what's 1 divided by a very, 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 very small number, almost 0? And what's 1 divided by a very, 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 very small number, almost minus? Just below 0, a negative number. So just let me give you a couple of minutes to have a think about what that would look like. And it's zero risk because you've got a whiteboard. No sneaky cheating on your calculator. Well done, Charlie. Spot on.
Huh? What did you draw?
That's what it is.
I think it's cheating.
Yours doesn't touch.
Oh. So Pat, what's 1 divided by 1?
1.
So I know this new graph is going to go through that point there, that's good. And 1 divided by minus 1 is that as well. So Harry, what's 1 divided by 0? It's not, no. If you do 1 divided by 0, you get a math error. You can't do 1 divided by 0. You can't do it. So clearly this graph doesn't have a value at this point here, or this point here, or this point here. So I'm going to do some dotted lines, because they're going to be asymptotes. Well, I'm not even going to do dotted lines. So what do you get? So what do you get, Charlie, when you do 1 divided by a very, 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 very small number? A very, very, very big number, that's right. And that's going to happen here and here. So what you get is a graph that looks like this. And the same will happen with negative values, but 1 divided by a negative is a negative because it's a positive 1 divided by mixture of x and minus. So you get that, and it will continue all the way along. In fact, I can show you. So there, oh, hang on. There's the graph of sine, and there's the graph of 1 over sine. And it has asymptotes here at 180 degrees, or pi radians, and 360 degrees, or 2 pi radians, and 0 radians, 0 degrees, and then minus 180 would be another one. This graph here, 1 over sine x, has a really nice name. Well, I'm lying, it's not a nice name, it's got a really odd name. It's actually called cosec of x. And it's actually an abbreviation of the secant. So sine is an abbreviation of SINE. Cosec is an abbreviation of cosecant, and it's just an old-fashioned word which we abbreviate to cosec. So why is sine x? Why is 1 over sine x is cosec? And your calculators will show you. We'll do this. Although you need to type in 1 over sine x. So fraction button, 1 on the top, sine x on the bottom. It hasn't got a cosec button. Now the good thing about cos x is that it is the same shape as sine, it's just shifted along. So the graph of 1 over cos x will have a similar shape to the 1 over sine x graph, won't it? It's going to just be lined up perfectly with the peaks of the cos graph, whereas that one was lined up with the peaks of the sine graph. So this time our asymptotes come at 90 degrees and 270 degrees, because that's the place where the cos curve is 0. The cos curve is 0 at 90 and 270, so those are the places where 1 over cos is not defined.
Is this one called sine x?
So this one is called sec x, which is an abbreviation of secant. Oh dear. Oh dear. Now,
I don't have the balls to say it.
I always think that's the wrong way round. You think 1 over cos should be cosec because it's got cos in its name. So can I give you a little trick to remember? Look at the third letter. The third letter of cosec is S, which reminds me that's 1 over sine. And the third letter of sec is C, which reminds me it's 1 over cos. And I still have to do that because it still seems the wrong way round to me.
Why did they name it that though?
Well, the names cosecant and secant are antiquated names, and I have no idea what their origin are.
Surely if you're just naming it, wouldn't you just name it the right way?
There is clearly a reason why it's named that way. I'm afraid I couldn't give you that reason. Now, tan. I don't think we'll spend a lot of time with the sketch, but I can show you what tan 1 over tan looks like. So let's get rid of the clause. So that's tan, and tan's always more confusing, isn't it? So I always think about it being minus 90 and plus 90, or minus pi over 2 and pi over 2. And cot, therefore, 1 over tan looks like this. So it's not defined when tan is 0. When tan is 1, it is 1. And as tan disappears off to infinity, 1 over tan goes down to 0. But don't worry about that at the moment. What I do need you to note is that if I do 1 over tan x, That's got a name as well. That's called cot x, short for the cotangent, which again, that seems to make a little bit more sense. And look, my little third letter thing still works.
Did you make that three-letter thing up?
Sorry?
Did you make that?
Well, do you know what? I did not. I never had a good way of remembering it. It was a student that pointed out to me. Now, whether they got it from somewhere in a book, I don't know. But that's this lesson does finish at 5 past, doesn't it?
I believe it finishes at 1 on the dot.
I thought it was 10. Yeah, 5 past.
Yeah, the last lesson finished at 10 past, and then 55 minutes long.
Yeah.
So we've met the 3 reciprocal trig functions. Shall we use those reciprocal trig functions to derive a new identity? Well, the answer is yes, we shall. Okay? Yes, we shall. So there are 2 identities which are referred to as the reciprocal identities, and they both start in the same way. They both start with our sine squared They start with that rule, okay? Now what I'm going to do is I'm going to divide everything in that identity by sine squared. Now, can anyone spot an issue with that? Well, you've just done, or I've just done, what I tell you never to do. Don't divide by sine x or sine theta, because it could be 0. So we're temporarily breaking that rule, all right? And I can justify why I break that rule in just a moment for you, all right? Now, let's see what we get by doing that. What is sine squared theta over sine squared theta?
1. -1.
1 over sine squared, well hang on a minute, that rings a bell. 1 over sine is cosec. So 1 over sine squared is cosec squared. I'm using theta, x theta is interchangeable. How can I write cos squared over sine squared? Well, I know that sine over cos is tan. So sine squared over cos squared would be tan squared. So is anyone going to be brave and say what cos squared over sine squared would be?
Tan square theta.
Well, no, it's the reciprocal of this. It's that flipped over. Remember, 1 over and flipping is the same. So it's going to be, this is 1 over tan squared, which is cot squared. Cot squared is 1 over tan squared, and that's tan squared, and it's flipped over.
You just added cot x.
Oh, sorry, cot squared theta. Theta.
I didn't know.
I've got 3 minutes, haven't I? Now, I can justify why I'm allowed to do that, divide by sine theta, because let me put the graph of sine up on the board, okay? Let's get rid of... that's sine. Now I've said, remember I said I'm dividing by sine squared theta, which I'm not normally allowed to do because it can be 0. But let me show you the cot graph. There's the cot graph. Look, when sine is 0, cot is not defined. When sine is 0, cot is not defined. So I'm okay because there's no way this can have an answer for theta that would be an angle that would make sine theta would be 0. So I'm okay for cot. What about cosec? When sine is 0, cosec is not defined. When sine is 0, cosec is not defined. So I'm allowed to do this naughty thing because I get an equation which couldn't have an answer that would make sine theta equal 0. Now, to be honest with you, you don't need to worry about that. It's just, and I taught it for 24 years until 2 years ago, someone said, why are we dividing by sine squared theta when you tell me I'm not allowed to divide by sine? That's right. So this is our first new identity, which we are going to use next week. There's another one that goes with it, and all will be well. Right, we need to get out of here quickly because Mrs. Clark